All right, everyone, thank you very much for coming to my talk, C++ Rvalue Lifetime Disaster. Even after 1 year of Corona, I still have to get used to talking to a wall, essentially, still. Still getting used to it, so I imagine you all being there. So it gets a little bit easier always if you talk to someone or just to a wall. So yes, again, thank you very much for coming. We are going to talk about C++ and R-values. The title is a tiny bit sensationalist, probably. You may ask, well, what's the big disaster? We're still all here. And besides a pandemic, we don't really have huge problems. Well, I mean, bear with me and we'll see what I mean. And then you can judge how bad it really is. It's maybe a small disaster. Anyway, let's talk about R-values, in particular R-value references. R-value references came about back in the days prior to C++ 11. We had the standard library, and the standard library was always very fond of value semantics and regular types. And the problem is that if you are copying these values, or if you're building containers from these values in the times before C++ 11 and before R-values, this led to frequent copying. And well, it was pretty obvious that to get the performance up, we would need to get rid of this copying. And the idea was, well, if we could mark up certain references as, well, this reference will go away pretty soon, then we could just take whatever resources that reference is holding on to, that object that is being referenced is holding on to, we could move these references, these resources over to the copy. And that would make copying a whole lot more efficient. And now it's not called copying anymore, it's called moving. But the idea is basically you take away the resources and you are more efficient that way. This is here an example. So say you have a vector of vectors. And whenever you would copy or when you append to this vector of vectors a new vector, then that vector would traditionally need to be copied. You can avoid that by using move, which essentially marks the vector as you can scavenge the resources from this vector, and then you can reuse them in the instance of the vector that's inside your vectors of vectors. And that way, the R-values help to mark up this, you can move from that object. Now, R-values got a different purpose over time, and that is for managing lifetime. Because R-value is not only meant to be something to be an R-value, it doesn't only mean that you can scavenge resources, it also means it will go away pretty soon. And sometimes you just don't want things to go away. For example, C++ 11 already started that std cref would only accept lvalue references. So it would not accept R-value references to be wrapped. And std cref is a wrapper for references, but indeed for lvalue references. Now for C++ 20, this became a whole lot more important with the introduction of ranges. Ranges are, for those people who don't know, are essentially two iterators that you would pass through an algorithm encapsulated into one object. And iterators or indeed these ranges, they are often references into another container. So you have a range, a view over an existing container. And if that existing container goes away, your iterators are dangling. And obviously that's something that we don't want. And C++ 20 uses R-values to prevent that from happening. Here's an example. Say we are having a vector, and this vector gets filtered, and this filter is actually a lazy filter. So the filtering doesn't happen right away, but the vector is referenced by a filter object that holds onto the reference to the vector and the predicate according to which we want to filter. And when you then start to iterate over the filter object, the filtering will happen lazily. And for it to happen at all, you need a reference to the vector. Now, in this particular situation, this vector here would be an R-value, and it's a temporary. And when you are actually finished with processing this statement here, when you are past the semicolon, then that vector will go out of scope and will disappear, and you would have a dangling reference in the filter. Now, the this is something that we don't want. And so C++10 says, if this is an R value here, the listed vector, which is the case here, then it won't compile. So you'd have to declare the vector basically outside and then just name it here, and then it would compile. Now, before we go more into this lifetime aspect, let's talk more about this move aspect, the efficiency aspect, because there are a bunch of, kind of as a warm-up, there are a bunch of tricky, like maybe a little bit tricky things to get right when you want to use it for that purpose. So here are the pitfalls for R-value references when it comes to moving. Now, that's our first example. You have a function foo, and you have a variable a local variable that is being returned by value. And we try to do it this way. We declare the variable const and then move it. And as many people of you probably know, that won't work, because you cannot move out of a const. The std move would indeed turn the a, which is an lvalue reference here, into an rvalue reference to a const a, because a is const, and you cannot move out of a const rvalue reference. So you get a copy. You don't get the efficiency gain that you would hope you get. Now you can correct that by making the a not const. That's certainly better. That's not as good as it gets, though. In this case, we do get a move. That's good. But there is one more optimization that C++ has built in. If you just omit the std move altogether, what happens then is you get something that's called named return value optimization. And the trick here is that the a that gets instantiated inside the local function foo, that local variable, gets actually instantiated already in the place where the output parameter would go of this function. And so you don't need to copy it at all. It's already created in the right place. So when you return out of the function, the a is just there. So in this case, actually, std move makes things worse. Let's make a const. What happens? Everything okay? Well, it turns out, yes, it is. It's still using named return value optimization. So the a internally as a local variable is const, but the outside a is not, which is fine for C++. It's okay. You can do it that way. It's a tiny bit dangerous, maybe, because let's look at this. If you now say, well, I just don't always have the same a to return, but for some condition, I have one a and that I create one way. And for a different condition, I have a different a, and I want to return it. Now, what happens there? Well, the return value optimization doesn't work in that case. It only works if you always return the same variable. It kind of makes sense because the compiler has to decide when this a is being instantiated to instantiate it in that special place of the return value. And it can only do that if it knows that this particular a is going to be the one that's returned on all code paths. And here it's two different a's, so it doesn't really know which a to put into the return value spot. Theoretically, with optimization, you could do it here, but standard says no. You need to always return the same a. And then you are back into const land, and you get a copy, not a move, because a is declared const. So okay, we take away the const again, and then we get a move. Now, let's make things a bit more complicated. Say the a that we want to return is part of structure. It's a member of a structure B. And we do this. We just create a B, and then we return b.ma, that member a that we want to get out of the function. What does that produce? A move, a copy? It produces a copy. So in this return statement, the B is not automatically becoming an R value. So it's only if this special role with return something turning into an R value only works really if you're really referring to a single variable. If you have a more complicated expression, it doesn't do that. And then it's just a regular BMA, and that's returned. That expression is not movable, and it's returned by copy. Now, in order to make it movable, you can write the move around the B alone, because then R values, if you have an R value and you do a member access to this R value, then that is actually an R-value itself. So you don't have to write the move around the BMA. You can just write it around the B, and it'll be fine. So here are the recommendations. Basically, if you return a variable, then make them non-const. That's important. And Clang, if you use it to compile your program, has a warning that warns of pessimizing moves and other problems that other misuses of move that you should enable so that the compiler will help you. Okay, let's talk about something else. Here we have an A again, and that's embedded in a structure B, and the A is returned by an accessor as an lvalue reference, const reference. And we write code below. We have a B, and the auto const reference A is B get A. And everything is quite normal. So you return and const lvalue reference, and the variable A, where that's assigned to, is also const lvalue reference. So nothing unusual. Now, what happens if you have an alternative? You have generic code, and you either have a B or a C, and you don't really know in your generic code. Sometimes you may have a B that returns by const value reference, a const lvalue reference, or you have a C that returns by value. And you kind of want to write generic code that handles both cases. Now, if you write this, you just always assign to an auto const reference. Does that work? Turns out, yes, it does. Because you have temporary lifetime extension. Temporary lifetime extension is a feature of C++ that is older than C++11. And we'll see just in a second what consequences that has. But it's older than C++11. It was kind of the attempt to do something that where the right thing happens. You can just always write a const reference, and if you get a value, then that would just magically work because that temporary that you're creating would get its lifetime extended until the reference goes out of scope. So that would fix it up, essentially. Now, let's see how this works in this situation. So we have an A, and our A is less comparable. And we have an accessor for two Cs that can produce an A. And we want the minimum of the two. Now, if we write that, well, does that work or not? Let's look at the implementation of minimum in the standard. And as you can see, it takes two lvalue references and returns one of them. And unfortunately, this minimum function kind of forgets about what kind of thing it is getting. Everything is being cast into a const lvalue reference. And then a const lvalue reference is returned. So in the particular code that we wrote up there, that A is actually going to dangle. The temporary lifetime extension is not going to kick in because it just doesn't know that there is a temporary whose lifetime is supposed to be extended. It just gets a constant lvalue reference and is happy with it. And next moment, everything goes out of scope and you have a dangling reference. Okay, let's try to improve on that. So first of all, we saw that everything is kind of the const lvalue reference. Once it's cast const lvalue reference, you don't really know anymore about the lifetime. You don't know anymore whether it was an R value, a PR value, like a value or R value reference. All that's forgotten, and we can improve on that by doing perfect forwarding. So that's what I did here with the little implementation of our minimum. It just takes the left-hand side and the right-hand side by a universal reference and then forwards. And if you do that with the code above, then our minimum would actually return an A R value reference. So something that indicates that the lifetime is limited of that what's being returned. Unfortunately, though, and here comes in that temporary lifetime extension is pretty old. The A still dangles because the temporary lifetime extension works if you are giving it values. So the values lifetime, these temporary values, they get extended. But if you give it an R value reference, then well, there's no temporary, there's just a reference, and you cannot extend anything. The problem is that C++, of course, the modern C++ turns, with perfect forwarding, turns values into rvalue references pretty quickly. And that's what happened here with the minimum function. And well, and then it doesn't work, it breaks. So what do we do? Here is another example where that's problematic for the temporary lifetime extension. Say we have a function foo, and in this case, we want it to return whatever another function returned to it. So we want to kind of forward the return of a particular function to the caller. And again, the sum a in this example may actually be a constant reference, or simply a value a. And let's see, if we want to do nothing in between, then it's easy. Then we just write decal type auto foo, and then we say return sum a, and then it will actually work. If sum a returns a value, then the foo will return a value. If sum a returns a constant lvalue reference, foo will return it. But let's say we want to do something in between. We want to add some code here, look into the a or whatever. Then what do we do? How do we do that? A bit problematic. So one simple idea would be, well, why not use the temporary lifetime extension, right? It kind of does the right thing. We said it's kind of the automatically doing the right thing functionality. And indeed, the auto const reference in that function, in case sum a is returning a value, would stay in scope. We wouldn't get a dangling a. The problem comes in when we return, because the decal type auto will look at the declaration type of a, and a is declared as a const reference. So the decal type auto will say, okay, that's great. Then I'm just going to return an lvalue reference, not knowing that the lvalue reference is only pointing to a valid value because that valid value got its lifetime extended. So temporary lifetime extension doesn't really work here. Alternatively, we could say, okay, why not change the foo instead of returning decal type auto? We could say, well, we can just have it return an auto. Well, auto just decays everything. It valuefies everything that you give it. So in this case, it would work, but foo would always return a value, even if sum a returns a const reference. So what's the problem here, really? The problem is that the temporary lifetime extension lies about its type. It's really when it's extending the lifetime of a temporary, that reference pointing to the temporary has really the properties of a value. It's the only thing that's pointing to the value. It's owning this value essentially, and if it goes out of scope, that value goes out of scope as well, and that's all the value does. But it doesn't say so. It says I'm an lvalue reference. So what do we do? I think we should throw away temporary lifetime extension. It just doesn't work in the modern generic code. What we really want is to say, well, is not to lie. What we want is we want to automatically declare a variable, a value, if it's a value, if a value is being returned, and a lvalue reference if an lvalue reference is returned. And that way, the code that is using that variable can actually reason about its type and can reason about the lifetime and do the right thing based on that information. So here's something where I try to do this. It basically says it's a macro, for better or worse. It's a macro for that auto assignment. It replaces this auto const ref a equals something with a macro. And what that macro does, it tries to find out the type of that expression that you want to assign. And if that type is either an rvalue reference or a value, then it will decay it. So it will turn it into a value. But if it's an lvalue reference, so its lifetime is long, then we'll keep the lvalue reference. So, and if we use it for our particular example here, then everything will be fine, actually. So we can do an auto cref, which is the macro we just defined. we can use it for that assignment that declares the A as a kind of the new-fangled auto const reference. And then we return it with decal type auto. And that will do the right thing because the decal type auto will adopt the type of A, and that type is either a value if some A returned a value, or an lvalue reference if some A returned an lvalue reference. Watch out, don't use parentheses here. So if you use parentheses, then what you're getting is not the declared value of a variable, but the expression type. And the expression type here would actually be an lvalue reference, even if A is a value. So it's one of these other pitfalls of C++, is if you write decal type with a double parentheses or a single parentheses. So yeah, so no parentheses here. We make autocref our default auto. It may seem crazy to use a macro for such a thing as simple as an assignment, but the idea that it kind of always does the right thing if you want to take something like a constant value efficiently from a function makes it attractive to use it, and it works well. For now, it doesn't work with that if that expression contains a lambda, but that will actually, or is fixed in C++20. Now, there is one little, well, peculiarity or detail that you can choose whether to make this decayed value const. Strictly speaking, the semantics of that what's being returned is const because it's generic code. So the sum A could either return a constant reference, which would be const, or a value. But semantically, it should not be modified in foo, because if you are doing this with a constant reference, it wouldn't work anyway. So if you want to write generic code, you must not modify A. We do that, but then you again have to watch out with the return. So if you basically if you want to return this variable, then you have to make sure that that you use a special autocref return, which is then what we had as the autocref before, without making anything const, not making the value const. All right, so let's see how that works with our minimum. So now we have kind of the second puzzle piece. We had this our minimum that does the forwarding. And if you combine that with the autocref, things actually start to work. So the our min correctly forwards the rvalue reference. And then the autocref correctly reasons about the type and says, okay, this is an rvalue reference. It's going to go out of scope pretty soon. I better make a copy here, or a move, in fact. All right, let's see. Let's use the autocref now for more stuff. So here we have a B that is an rvalue reference, and or a value. It's a temporary right here. And we want to assign one of the members inside B, again an A. And in this case, the MA is going to be an R value because its members of R values are R values. And so this will work because this is the type of that is a R value reference, and then the autocref will turn it into a value. So all good. But very frequently we don't program this way. Very frequently we have accessors, right? So they actually, well, we don't want anyone to modify our MA, so we just write an accessor. And then we write the same code with the accessor. Now, does that work? Unfortunately, it's a bit problematic because the decal type of this thing is, of course, the return type of getA. And as you can see, the return type of getA is a const reference. It's an lvalue reference, not an rvalue reference. And the getA can be called on B, which is an R value, creating a temporary B, and we can call getA on it. It's like, well, but I don't really want that, right? Because it would be nice if we could only call getA on lvalue references, on B's that stick around, that don't go away. And then I can safely get a reference to the A inside the B because I know the B is going to stick around. Well, one thing you could try is you can add an ampersand here, which is now valid, but it still doesn't work because it still basically says I'm gonna this here is gonna be something that binds to const lvalue reference, and const lvalue reference binds to anything. It includes rvalues. You can bind an rvalue to a const reference, and this is really bad, I think, because it will affect any of these accessors which are written with a const qualification, with a const reference. We have the code is full of this stuff, right? And I think that's a problem. So let's look at this a little more. I call this actually rvalue amnesia. Why do I call this rvalue amnesia? I call this rvalue amnesia because the going through get a, C++ forgets about the rvalueness. It just binds to the lvalue reference, and then the rvalueness is gone. And all we have is lvalues, and the lvalue is always good, and we think it's a long lifetime, but it's not. So let's see how other parts of C++ deal with this. So we, of course, have the ternary operator. So with the ternary operator, you can take two references and return one of them. Well, what do we get? So let's say we have a constant lvalue, right? On both sides, on the left side and the right side. So it's LL. L is the one that returns the lvalue reference. And then you get an lvalue reference. Fair enough. Now, what if you have two rvalues? Well, no big surprise here. You get an rvalue reference. All good. But what happens if we mix the two? We mix the rvalue reference with the lvalue reference. What do you think? Get an a const. Isn't that weird? So C++ decides, I'm gonna make a copy here. I'm going to the type of that expression is gonna be a value, which means I'm copying either one reference or the other reference. And you kind of think maybe they already knew that there is a problem because they wanted to work around and say, well, probably make a copy just to be safe. Now, C++20 has something similar. It's not the ternary operator, but it has a common reference trait, which is actually used for if you have ranges in C++20. And then you can combine these ranges. For example, you can concatenate them. And that resulting range has to have a reference type. So you have essentially two kinds of iterators. One iterator comes out of one range, and the other iterator comes out of the other range. And they both return a reference. And now you want to have the common reference of these two. And this is exactly what this trait is being used for. So again, let's say both iterators return a constant lvalue reference. We get a constant lvalue reference. Likewise, with rvalue references, two of them, we get an lvalue reference. Now, what if you mix them again? What do we get? Well, in this case, I decided, hey, we get an lvalue reference. Kind of logical because an rvalue reference binds to an lvalue reference, but the lvalue reference doesn't bind to an rvalue reference. So we take the common denominator of the two and say, well, it's an lvalue reference. So of course that again goes against is basically embracing rvalue amnesia. It forgets the rvalueness. So let's do the same thing with values. You have an a const and an a const ref. Well, then it's actually an a. So there it makes a distinction. The common reference makes a distinction between references, rvalue references, and values. Yes, so common references really loves rvalue amnesia. So that begs the question, what is really the problem here, and how should things be? What is correct? Let's look at this little diagram. So we essentially have four kinds of references: constant and non-const, and we have L values and R values. And the mutability also comes in two different flavors. One is immutable, one is mutable. And There's one more aspect, which is actually the rvalue reference has this added property of that you can scavenge from it. You can steal from it. That's an added benefit of having an rvalue reference. You can't do this with an lvalue reference in particular. Okay, so what kind of conversions are now allowed in C++? Here they are. So the constant lvalue reference takes everything. It binds to everything. And the constant rvalue reference only binds to rvalues. So this is the current state of the art. And you can see that it has a problem because it goes from a short lifetime to a long lifetime here and there. And that kind of doesn't make sense, right? What we really would want is this binding behavior. So you always go from long lifetime to short lifetime. So you don't promise more than you can deliver. And you go from mutable to immutable. Everyone who gets something mutable can always say, okay, it's immutable. It's not a problem. The opposite, of course, is a problem. But likewise is going from a short lifetime to a long lifetime. You have to go the other way around. So, and yes, and you cannot go from lvalue reference to rvalue reference because you are missing that scavenge. Okay, so that's why I brought it up, because that kind of forbids that kind of binding. So as a summary, only lvalues should bind to const reference, but anything may actually bind to const ref to the rvalue reference, const rvalue reference. This is sad. It's very sad. So we dug ourselves a hole, and now we are in there and don't really know how to get out. Now, I want to make a suggestion of how to get out. Okay, I want to see if there's any fix that you can imagine. These are all only ideas. I didn't implement any of that, and before this can be called like a real real solution to the problem, certainly we have to try it out, and we have to try it out on a big code base and see how it goes. It's only an idea. And here's the idea. First of all, what are the requirements? I mean, existing code has to continue to work. There's no way that we can actually break existing code. The existing libraries must also work when they are used with new code, because we may write new code, we want to use the solution to the problem, but we cannot afford to change all our libraries. So we somehow need to gradually introduce these new binding rules within one single code base. The idea would be that any reference you have in your program either uses the new binding rules or the old binding rules. Now, the good thing is that reference binding only happens at the beginning of the lifetime of a reference. So once a reference exists, it doesn't matter anymore how it came about. You don't need, when you're reasoning only about the type of a variable, then whether that was bound by the new rules or the old rules doesn't matter anymore. It's done already at that point. So essentially, what I came up with is have a pragma, have something that basically switches these binding rules on and off. And whenever you are, say, include any library, then you could go to the old binding rules, include that library, and all the references that are declared in that library would adhere to the old binding rules. And when you then switch on the new binding rules, all the references that are declared there would adhere to the new binding rules. And you can go back and forth and have groups of variables either be in the new binding rule camp or the old binding rule camp. So in order to jog a little bit our memory of what kind of declarations I'm talking about, I made a list of where references are declared. First of all, you have local or global variables. You have structured binding, very similar. You have parameter lists. So you have declarations of functions that contain references in their parameter lists. Then you have structs, which have references as members, and they may be initialized as PODs. Then you have references that are initialized in constructors of structs or classes. And you have lambda captures. I didn't come up with anything else. If you have any more ideas, I'm happy to hear them. Now, so let's say with these pragma, you can opt in or out of the new binding rules. So the effect would be that if you say, okay, I'm declaring an A that takes an int const reference, and I switch on the binding rules and I declare a B with an lvalue reference and a C with an rvalue reference, and I switch off the new binding rules again. I would suggest if you then try to define the B that you declared in a different way, then that will be an error, because you're kind of expecting the int const reference to bind in a particular way, and if you're not consistent in the declaration and the definition, that would, in my idea, an error. The effect would be that if you call A with a 5, which is the old binding rule, that works, but B with a 5, which is the new binding rule, it takes an int lvalue reference, that wouldn't compile. While your new lvalue reference is the rvalue reference, that now binds to everything because it doesn't get any more promises. It looks a bit strange to me as well, but that would be kind of the most general reference again, probably used in many places, and that would again compile when you're plugging an rvalue reference, but it would also compile when you give it an lvalue reference, which we did down here. Okay. What would I thought a little bit about what would be the impact on the standard library. Of course, we would need some sort of feature test macro if we have this new reference binding facility. Functions are by and large can be implemented equivalently, because you can always, use instead of the const lvalue reference, you would use the const rvalue reference for this catch-all parameter, where you just want to take something by reference. Something that would need to change is the common reference in the type traits. There, the rules would obviously be different. You don't want to have rvalue amnesia. I didn't see any other type traits that would be affected. So, of course, we don't have that all. So we cannot say, well, that problem is solved, and I think it probably won't get solved. It's something that's in the standard. It's legacy C++, and we probably have to live with it. What can we do? Well, I suggested a few mitigations. We can say, well, we deprecate temporary lifetime extension and have something like auto cref that sometimes helps. Then we actually use for member access, we don't write regular member accessors. We build a little macro that deletes the rvalue reference overload, so that we can be sure that when these accessors are used, they're not used on rvalues and give surprising results. Here is a new common reference. It's essentially like the old common reference, but the std conditional down here essentially says, okay, if somewhere in your list of types you have an rvalue reference, then really your type should also be an rvalue reference. We add the rvalue reference to it because we want to basically designate that this is something that goes out of scope, that has a short lifetime. When you are looking at we talked about the lifetime, the rvalue amnesia with the ternary operator, where it returns an A const and it forces a copy, which is obviously not efficient. You can do better. So if you're using the common reference, you essentially, that we just defined in the previous slide, you can, before you employ the ternary operator, you could cast the two arguments to a common reference according to the common reference we defined, and you can package that into a macro, and then you at least get something efficient out. So that if you have an rvalue reference and lvalue reference, that would return an rvalue reference, which doesn't make an immediate copy of one of the two references. It's more efficient that way. All right, here's the summary in the top of the talk. I think the const lvalue reference should never have bound to R-values. It's a historical accident. Fixing C++ is possible, maybe, but I haven't demonstrated it. We certainly would need an implementation, and we would need a large code base where you can prove that this would actually work in practice. And until then, all that's left are mitigations that we can use. thank you very much for listening. And if anyone has questions, go ahead. Yes, it was meant to be a 90-minute session. So, but I'm done with the material. So if you have any questions, you can stick around, and I'll answer any questions you may have. We use all the mitigations, all the ones that are listed. We have auto cref, we have the conditional, we have, we can go through them again. So here, mitigations, yeah. So we have the auto cref, we have common reference, the ternary operator, and we also have the replacement for the member accessors. So we use all of them. I don't have much experience with Rust, but I mean, clearly the idea of using these rvalues as lifetime, as having a meaning in lifetime, is an attempt in C++ to emulate something like Rust. It's certainly going in the right direction. I don't have a strong opinion on Rust because I haven't used it myself, but certainly the idea is right, and here we are trying using rvalues doesn't go all the way there, but a little bit of the way, and it's very tempting to use that, and then C++20 does it, except that as I've said in the talk, it doesn't quite work. Well, no, I mean, if you can't just change the const lvalue parameters to const rvalue parameters. And I'm going here for questions. So the question was, is the const lvalue parameter, if you change const lvalue parameters to const rvalue parameters, and adding an rvalue overload, and rvalue reference overload, enough of a mitigation? Well, I mean, this whole mitigation doesn't, the const rvalue reference taking everything only works if you are, using these new binding rules that I postulated. So that doesn't work in C++. You would need to have this fix that I kind of had these illusions about, and it's. The only thing that you can do now is basically say, okay, I have an accessor that is only working on lvalue references, and I delete the rvalue reference. And that way I can at least can't accidentally be called on an rvalue reference. And if you're called an rvalue reference, you have to come up with a solution. You have to maybe make an rvalue overload. Okay, I'm supposed to explain how the common reference works in a bit more detail. Is not, I think, where do I have it? It's not terribly difficult. So essentially here, the old type is the old common reference. And then if that old type is an lvalue reference, then there's kind of the danger that this is an lvalue reference accidentally. And then we check, is there anything in our parameter list that is actually an rvalue reference that we just turned accidentally into an lvalue reference? And if that happens, then replace the lvalue reference with an rvalue reference. Okay, any more questions? Yes, I will make the slides available. There's a question is whether I make the slides available. Yes, they will be available. Okay, first one, you can. Well, so the question, one of the questions here is, and let me go back to the diagram to answer this question. So these are the change it, or these are the binding rules that I propose. These are the existing binding rules, and these are the bounding rules that I propose. And one important thing here is there is no arrow from lvalue reference to rvalue reference without const. So going from a reference to a const rvalue reference is actually fine, because you cannot move out of the const rvalue reference. And when these things were introduced, I asked myself, well, what is this const rvalue reference actually for? Why do we have it at all? But this is here it becomes pretty clear. So this scavenge risk only appears with rvalue references, mutable rvalue references, not with const rvalue references. So going from an lvalue reference to a const rvalue reference is actually perfectly safe. Binding rules. Someone is asking for binding rules for the auto ref equals a foo. You are so if you have basically the temporary lifetime extension for auto ref. So when we are going back, I had this temporary lifetime extension on the other slide, and I'm going to go back to it. Here, for example. So would it make any difference if we have an rvalue reference here? So auto ref, auto ampersand. No, it doesn't really make any difference, because the temporary lifetime extension is still going to work the same way. It will work. If some a returns a value, then the lifetime will get extended. But if you then ask for the type of a, then you would get as best an rvalue reference, which again is wrong, because the a here would be dangling. So here you get an rvalue reference, because some a returns a value which gets bound to an rvalue reference. Then you return the a here, but then the decal type auto would say, okay, then it's an rvalue reference, or actually would probably even say it's an lvalue reference, because if you declared it as an rvalue reference, but if you access it like this, just outside of without a move, then it would actually be an lvalue reference. So it doesn't make any difference.